All right, let's get started. So today there's a new topic, although we started off a little bit last week. Hold on. Yeah. And that is a very important concept of the economic surplus. In the introduction, I already talked a little bit about it, how the surplus was created in 10,000 BC when the first farmers were there. They were making their first surplus food, more food than you can shake a stick at or eat in this case. And then this gets traded, and then you get the creation of trade, markets, money, war, civilization, the whole shebang, everything that characterizes us and economics. That will not need repeating. What this lecture is going to be about is that we're now in a position to show you that the economic surplus is analogous to what is called the kinetic energy in mechanics. Okay, and this little graphic here is sort of a summary of what's going on. This one I just got from Wikipedia. You can look it up yourself. And you can see that in Wikipedia, they define something that's a producer surplus, which is the top part of this demand curve, this area. So if you take this demand curve, so forget the fact that it's not straight. Forget the fact that it's not straight. Those are some non-inertial forces or other forces that are working on it. You'll see that that corresponds to this part of the graph if you just have a regular momentum velocity graph. Now, you can do all your switching around. You know the quantity demanded goes the other way from the quantity supplied, so you flip this. And then the price is negative, so you flip it again, and then you'll find that the consumer surplus ends up over here. So really here there are three masses in this thing. There is the supplier, the seller, there's the buyer, and then here, this is their point of zero. This is the inertial reference frame, okay? I put two of these masses together, just assuming this is nice. I don't know, you know, at least the slopes are the same. All right, so this is what we're going to try to do, and I'm going to try to convince you that this actually works and that you'll end up with all the right notions and everything. And we'll talk about power, and we'll talk about kinetic energy and kinetic co-energy and all these things. Now, before I get going, I'd like to just ask people, like, kinetic energy is a little bit like action and reaction. It's one of these things that everybody knows that it knows what it is, but they're always mistaken. Now let me ask you, let me ask some victim what they think the kinetic energy is. Koen-Jan is all the way at the top there, so he looks like an appropriate victim. Koen-Jan, if you had to write down the kinetic energy of a mass, right, what would you say? Huh?
Like kinetic energy is 1.5 times 10 times E squared.
So this is what you would say is the kinetic energy, right? Right?
Yes, that is the kinetic energy of mass, yes.
Right, Max, do you agree with that?
Yeah.
Berend, do you agree with that?
Yes.
Yes. Quinten, do you agree with that?
For a single mass, I agree.
Yeah, okay. Who doesn't agree with that? 1, 2, 3, 4. And Wouter. Wouter, you don't agree with that, right? Huh? Why? What is it according to you?
Half P squared over
So Wouter says this, and I counted a bunch of people here that agree with him. You didn't agree with him. You agree with this one?
Yeah, I agree.
Yeah, this whole room agrees with Wouter, right? Huh? So there's a difference of opinion here. Now, are these the same? Well, if you assume that this is the case, and you plug that in there, then they're going to be numerically the same. All right? So you could be forgiven, you'd think. It's the same thing. But it isn't, right? Because look at that. What is this thing? Well, you'll have to do an integral, huh? So you'll do this integral over v. So this is a function of v. So you'll do this integral. Huh? And this is mv. And then this is actually this area, right? Okay? Everybody follow that? And I just said that the kinetic energy is this area. Now you would say, what does it matter? These numbers are the same. But it matters a little bit. Now what's the problem here? If you have a mass, what's the independent variable? Is that momentum or is that velocity? Wouter?
Velocity is dependent on momentum.
Yeah, velocity is dependent on momentum, right? Think about a mass. How you change its velocity? You'll have to apply a force. What is applying a force? That's changing the momentum. That's what Newton told you, right? So you can change the momentum by applying a force over some unit of time. That's the impulse, right? And with your new velocity, what you're going to get is the new momentum. You're going to have a corresponding, the mass will respond with the velocity, okay? And so it is in economics, right? So if you take the demand line, it looks like this. Oh, well, it looks like this, so there it is, right? And this is a little bit confusing, but this is the independent variable, and this is the dependent variable. Okay, so you would do a price change, and then the consumer, the buyer, will respond by, if the price goes up, by buying less. Okay, and if the price goes up, the seller will respond by selling more. He doesn't go and sell more and then figure out what the price is going to be. He can't do that. Right? So you can't take a mass and just change its velocity. You can't do that. You can't do an instantaneous change of velocity anyway. That will take you an infinite force. So you can't do that. All right? So if that's the independent variable and the energy should depend on the mass, then the only choice is to make the energy depend on the independent variable. So it's got to be this, right? Okay? It doesn't make any logical sense otherwise. Now, I agree with you that if you plug everything in, you'll get numerically the same answer, but that doesn't mean that it's the same thing just because two numbers are the same. Now, I agree with you here that also the units are the same, all right? But nevertheless, they're different things. I mean, the units of potential energy and kinetic energy are also the same, but then they're not the same thing, all right? So this is point number one. This is the kinetic energy. Why? This is the independent variable, right? Okay, everybody sees that now? That this is a mistake to think it's a half mv squared? In fact, that's called the co-energy. And we'll come to it, what the economic meaning is. It's all about for this lecture. All right, so that's point number one you got to see. So what does this mean? If this is the economic surplus, then the economic surplus is going to be a function of price. Now that makes a lot of sense, of course, right? Because if you have some goods and the price goes up, then you'll have more surplus for the same stuff, all right? A profit, surplus, profit is a kind of surplus, will depend on the price, okay? All right, we'll see all this. So, with this in our mind, let's get going. So, Another question. What are, Kunjan, you're the first to go. Since you got the first one wrong, what are the units of kinetic energy? This is not a trick question. He froze. Berend, what are the units of kinetic energy? Can you tell me?
Microphone. Yeah, you have to unmute, Kunjan.
Like n to the power of 10 and divided by v.
Oh no, the units. You don't know what units are? De eenheden. Wordt het in Newton gemeten? Wordt het in watt gemeten? What are the units? How do you measure it?
Newton.
In Newton?
Nee. Sorry, Joule. Het is gewoon Joule.
Joule. All right. Okay, thanks. All right. Now, what are the units of economic surplus? Huh? Can anybody tell me? Berend, can you tell me that? Price? So it has units of price squared divided by m, but you can say it's so it's price squared divided by m are the units of price squared divided by m, right? And p divided by m so is units of price times the quantity, right? Huh? So that will be just the units of price, and the units of quantity is, this is what you wanted to say, right? Huh?
Yeah, I said price per time, but...
No, that's not right. Huh? Huh?
Okay.
No, this is right. Huh? So I just kind of worked it out. We'll get to this, but I just wanted to put this in your head. First of all, that you were wrong on the kinetic energy, and secondly, that you got to get in your head that the units of the economic analog, whatever it is, we're going to show it's economic surplus, has units of some currency per year or per day or whatever, right? Now, this is a little bit counterintuitive. That's not what you would expect, right? Because in mechanics, we think of energy as being stored somewhere. It's just sitting there like a bucket of water, right? Now, in economics, when we think of something measured in dollars per year, that's not something that is stored, that is like a bucket of something, right? So it has a strange feel that this will be the case. But yet it is. Right? So this is one of the first challenges you have to overcome, is that you can see a flow like this, a flow of money, as sort of a stock. There's something you have. You have this income, or you have this surplus. And the fact that it goes over time doesn't subtract anything from your entitlement to this stream, okay? Berend, you can turn off your microphone now because it makes a lot of bonking. Huh? Thanks. All right? So we'll work through this, why this should be the case. But it's the first mistake you kind of make. There's a second mistake. The first mistake is to think that kinetic energy is a half mv squared, so that the economic surplus would depend on the quantity demanded, right? It doesn't. It depends on the price, all right? And the second mistake is to think that it must be measured in dollars or euros rather than in dollars per time, all right? Okay? So the surplus is a flow of money. Okay? So I just wanted to clear those two misconceptions up and then proceed. So I want to go back to last lecture where I introduced the ideas of work and power. And I just want to quickly go through there. This is traditionally the way energy was defined. It started with Leibniz's idea of a force as being a force that is applied over a distance rather than a force that's applied over time, as Newton saw it, okay? And this was called work. And what people had in mind was like this type of scenario, right? With a horse kind of pulling. So in economics, what we have is that a want or a desire that in Newton's interpretation, if it's exercised over time, gives you the willingness to go buy something. If you have your desires mounting up over time, you get the willingness to buy something. But in these situations of when you do it over the commodity itself, it's a realization of the want. So you have the want or the desire for the goods, and you multiply by the amount of goods that you're acquiring. All right? So we call this realizing the want, rather than creating the willingness to buy. All right? So what will be a nice way, and the terminology that Marshall uses is that this is what people want to do, and they call it to satisfy yourself. So if you take a want, this is your want, and then you realize it by multiplying by this amount of goods that you get, that you realize it, and that's a way of being satisfied, okay? So this satisfying has units, right? Because there's want, so let's just work it out. This thing has units of currency per item per time, and this is just units of, so the product obviously has got units of, you multiply this out, okay? So satisfying, okay, or satisfaction has got these units, right? So you're satisfied if you get more money per higher income. All right? Now let's give an example of this. Like, what will be an example? Now, one of the things that what I'm thinking of this is a handling fee. And if you take some goods, in order to move them from one place to another or give them to you, you got to handle them. Now, what do you pay? You pay so much per good, per lot, per unit of time. This is also what Adam Smith had in mind when he was looking at the labor theory of value, right? So he's looking at the amount of income associated with work. Now you can measure work in terms of the labor, but here I'm just measuring it about the labor that goes into delivering some product. Adam Smith, he looked at pins and pin manufacturing, okay? So you have some people, and they're working at this pin thing, and you have to pay them so many pounds per pin per day, all right? So that will be the fee, and then if you then multiply it by the amount of pins that you put through, and you deliver, then you can calculate this satisfaction. All right? Now, rather than just looking at an amount, you can look at an amount per unit of time here. So that's just your output. And then you can look at the rate at which you're satisfying yourself. So this is what also is cool, and we've been calling the fulfilling your wants, right? So this is this idea of filling, right? So you're putting out these pins, and then you multiply it by a want, and then you fulfill the want. And then these are just your sales amount, and you multiply it by the handling fees, and then you get some other number. And this is with the power, right? Okay? So here's an example how this might work. And what I wanted to do with this picture is show you how this relates to the way power was developed in mechanics. Now, power is a little bit of a strange animal because the only people who use them are engineers. If you look at physicists, they hardly use power. And if you look at the mathematical tradition, Lagrangian mechanics, power is not even mentioned. Okay? So it was invented by a guy called James Watt. And he invented this engine. It was a steam engine in the Industrial Revolution. He tried to sell it to people, but nobody would buy it. So what they would do, they would have these mills, and here is an example of a mill. So the mills were for grinding things, you know. And later on, they started using these mills for making yarn and for making clothes and other things. So it was a source of energy. So they used the windmills. In Holland, it was used for pumping water. But in England, in the Industrial Revolution, they used these water mills or these windmills for turning out goods and other that was a source of energy. And of course, if you don't have any water flowing fast, or if there's no wind, you've got to get your power from somewhere else. So what they would do, they would have this, these horses, and they would just turn this mill. Okay? And then every horse could deliver a certain amount of power. That's what they said. So this horse was pulling with some vector F, and this thing is turning at some angle of velocity, which translates to a real velocity here. And then every horse would deliver the product of the force times that velocity. All right? This is just what he did. And he was able to convince some people who had these mills that if they would buy his engine, they could replace so many horses that he thought were equivalent to it. And he would characterize his engine as so many horsepowers. Okay? So that's where the idea came from. So in theoretical treatments of mechanics, the whole thing isn't used very much. Okay? Now, how do we translate this into an economic engineering framework? Well, this horse, sometimes they even put people here, by the way, right? That was before they had horses. You know, there's some poor guys in the Roman Empire who were pulling this because these horses were too expensive and you could get slave labor for free. But anyway, you can think of these horses as doing the applying this handling fee, all right? So they're moving these goods along, all right? Okay, and the power that these horses deliver is, the equivalent to how you can multiply the handling fee by the sales that you're putting out to get the total satisfaction rate for your customers, okay? So if you're selling stuff and you want to satisfy your customers, then this is the kind of picture you can have in mind, and it all works out. Now, what are the units of power? Well, it's also easy to figure out, and it's always something you got to worry about because it never really gets intuitive, right? That's the units of the want or the desire, and the units of the sales or the quantity is this. So what you get is dollars per unit of time squared, okay? So whereas the work, and we can think of this also as the economic work, right? It's just the handler does all this work, the handling fee times how much he has handled, right? Well, it's not a bad name, huh? And similarly, power is not a bad name in this, so much manpower you would need in order to fulfill these wants of your customers, right? Huh? Well, these things are not so bad. Huh? Of course, horses are not going to be really good at making pins or anything, but putting them in boxes. But maybe a robot is, and he can get the fee. All right, so you see that, as you should expect, that this is the derivative, there's another unit of time here in the denominator. All right? Okay, so this is just sort of a recap, and it's a nice way in which you can see that work and power, as you know it, are totally equivalent in economics, and maybe even easier to understand. Huh? Okay? So here I have just work with a constant fee where you're displacing some products. And then if you multiply by the sales, you'll have the rate at which you're satisfying your customers. Now this is kind of the picture you have in mind. So let's take this picture and work it out in detail. And what I want to do here is show you that these were just a bunch of definitions, all right? So why would this be of interest, this work and this power in economics, okay? Realizing these ones, and then the rate at which you realize, why is this of interest? I mean, all we have is demand, right? So why are we coming up with something new? And this was also a problem in mechanics, you know, because there were these, we had this discussion last time, there were these two approaches to force. One, Leibniz, who says, well, a force is there to do work, and Newton, which is, well, a force is there because of the dynamics, because of the motion. Now, why are these the same, you know? And then everybody had to admit that the thing that was most fundamental was motion. And the notion of work was just more or less something that somebody had come up with. It was interesting to see what it was, but it wasn't really fundamental. There were no laws yet of energy or things like that, conservation. In fact, they felt energy was not conserved, because if you did work, then the work went into plowing that field, and then it just disappeared, and it wasn't gone. So they didn't have a notion of energy conservation yet. That came much later, all right? So really, what should have happened was the other way around. You first should define kinetic energy, and then from that you can figure out that this is equal to something you would call work. But that's not the way it went, okay? So they first had this idea of work with these horses and all this stuff, and then somebody comes and figures out what a force is, and then they started figuring out that the work would translate to a change in kinetic energy, all right? Now, what I want to do is follow this historical approach here and show how we can get this change of work, how we can make this equivalent, okay, in economics. And this equivalence between a change in the kinetic energy and the amount of work that's done is also called the work energy principle. All right, so what we're going to do is look at this a little bit closer. So I took this picture that I showed you last time, you know, where the credits are on the right side here, and the sales, the output, or the quantity supplied is on the right side, is the plus, and the negative is the debit side, huh? And that's the demand side, right? And it's the supply side. Well, this is the positive price. These are the sales that you're making. Then this distance, you can see that as the accumulated sales for the case study came from there. All right? Huh? Now, here is the market. This is the market, right? In this case, the seller is moving, the individual is moving that way. That makes him into a seller, and the market into a buyer, right? Now, what's happening? The seller is selling these items to the market by lengthening this, this distance here, right? Where you can keep track of that. Huh? And the amount of the sales is this vector. That's the rate at which he's lengthening it. But to do so, the buyer is going to charge him, let's assume that the buyer does that here, a handling fee, all right, to get these things over there. So this handling fee will end up debiting the seller, all right? So what is he debiting? He's debiting an expense, of course. Huh? An expense account is an account of type debit. Huh? So when your expenses go up, you debit the expense. All right. Now, you know, accountants will have some expense account called handling fees or handling and transportation fees or something like that. All right. And they will debit that. So this is on the debit side. The force acting on the, or the want acting on the seller is on the debit side. Yeah. So similarly, there will be a credit force on the buyer. I haven't shown it. All right. So what is this want going to do? Well, it's going to reduce this price, obviously, right? And it's going to discount the price. That's the only way it can go. So the seller has to give something up. It has to discount that. So the premium that is involved with the handling has to come out of the price that he is getting for it. All right? So that's what you do with a handling fee or a brokerage fee or whatever mediation fee. You take them out of the price. Huh? Okay? So if you work through that, then suppose I now calculate what the amount of realized wants are, all right? So I can easily say that the work that this handling fee handler does, all right, that's FDQ. I'll just look at this, since I have the velocity available here, I'm just going to take this derivative. So I'm going to divide this by dt and multiply by dt, all right? So I'll get that here's the power times dt, all right? But then I know from that this force that's debiting is going to have a credit component that's going to lower the price, right? The other way around. This is a negative force, so that effect has to be negative, all right? So this is going to be equal to that, and then all I do is realize that VDT is P dot dt is equal to dP, all right? So where I'm crediting the expense here, wait a minute. Yeah, I did this the wrong way around, but whatever. You got to debit the expense, and then you debit your loss. This is the loss, all right? Well, let's not worry about this for a moment. But, well, I switched the sign because I took this to be positive. I see what happened here, but whatever. Don't worry too much about it. Huh? So this is a loss that you're going to make on the sale, right? So you discount the price with a little bit on this. This is a positive movement, but there's a minus sign there, all right? So you debit this loss, and you're going to debit this expense account. So this should have been debit. My apologies. Even when you get debits and credits all sorted out of your head, it's so easy to make sign errors on these things, okay? All right? So it's as if this handling fee, if you look at the books of this seller, he's going to have some kind of credit here, which is the, so here's going to debit, and that's why I said credit over there. I just switched to the other side of the books. It's like, kind of get irritated myself because I get confused about the things that I'm telling you not to be confused about, okay? But anyway, this is correct. Huh? So he has to take a loss on the sale to pay for the handling fees. All right, that's the point. Okay, so the losses are equal to the expense, the regular expense. That's what this thing is saying. And because of the minus sign here, I got myself credited and debited a little bit wrong, but that doesn't matter. All right, so you can see how this goes. This should be an and sign, but they don't come through on Beamer. So the gain is this thing, and this thing is the power. So you see that's the power to change the price. So that's actually the sort of a pricing power that you can get. A nice way to look at it. Okay? Any questions about this? There should be, because it makes no sense what I'm saying. But I think it's okay.
Yeah, I missed the time.
Oh, that's interesting. Yeah, so what is this thing saying? This is actually saying FDQ is equal to minus VDP. Another way you can say that right? So there's no time in here. The time just showed up to go from VDT to DQ and from P dot DT to DP, that's all. The time could have been anything. It's just some parameter, all right? So what you're saying is that the credit, your expenses are going to translate as a capital loss. All right? So there's no time component. What is this thing called, this equation? In mechanics. Does anybody know? Yeah, but what is it saying? This is something, some change is zero, right? It must be a conservation principle, because if I take an integral, I'm going to get a constant, right? What is this law? It's a law of conservation of energy. Okay? So law of conservation of energy just follows out of this business of debiting and crediting here, all right? This is how they were able to prove the law of conservation of energy from Newton's laws, all right? So the third law tells you that some forces are the same. If you multiply them by a distance, you're going to get work is the same. And the second law is telling you how a price change, affects a force. And now you'll see that this is the work, the total work, plus the total kinetic energy is going to be the change in the amount of work plus the change in the kinetic energy is going to be zero. All right? It's the law of conservation of energy. Now I want to come back. I'm saying this because I want to answer Joris's question. He says, what has this got to do with time? Now I'm asking you again, what has the law of conservation of energy got to do with time? Nothing. In fact, the right way to look at conservation of energy is that it's the thing that emerges because of the time invariance of our laws. All right? Okay, because what happens is if our laws of motion were not time invariant, then at another moment of time, things would just look a little bit different. Okay, other amounts of energy will be needed to get the same physical results. All right, now this cannot be the case, because if it were the case, our laws would be no good. So what we posit is that this is no change, and then you can prove that this implies the law of conservation of energy. But here you see it in action. Okay, so time is irrelevant for this thing. But this is, of course, only mechanical energy. If you look at the energy loss per unit of time, friction, and we'll get to that, then time all of a sudden starts playing a role, right? So the answer to yours question is, why did I lose time? Well, because you have energy conservation, all right? By the way, momentum conservation, every conservation principle comes from an invariance. So energy conservation comes from the fact that the laws of nature are invariant of when you apply them in time, all right? What about the law of conservation of momentum? What invariance is that? Huh? Does anybody know? Yeah. Yeah, so you can translate the whole thing, your laboratory, to somewhere else, and it does the same thing. Now, how can you see this in economics? Well, we saw with momentum conservation already, the demand curve, here you got your quantity demanded, and here you got price. How does this depend on the amount of sales? It doesn't. It just depends on the velocity, independent of where we are. This thing doesn't really matter how far it is, right? So your behavior doesn't depend on how much you sold in the past or are going to sell in the future. Huh? Unless you built that in, of course. But Newton didn't build it in. That's the whole thing of space. Every point is the same. You got to hang on some springs and other stuff, storages, and I don't know what, in order to get the space dependence. That's very right. So the law of conservation of momentum tells us that the space, all points of space are equally on an equal footing. The laws cannot depend on where in space this takes place. Same thing, the law of conservation of price, or credit as debit, tells us that it's independent of how much somebody has already sold in the past, now, to determine how much he's going to sell now. Because demand and supply is the only thing that determines price, and not how much he has delivered. All right, and demand and supply are these flow variables, okay? And flow variables do not depend on where you are. Now, and so it is with energy. So whereas Newkirk gives us this idea of conservation of momentum, if we combine him with Leibniz's idea, we get conservation of energy. But all that says is that at a different moment in time, we should you should get the same stuff, all right? The handling fees should be the same. The losses should be the same. You can't all of a sudden make more losses or start paying more handling fees. Now, of course, this could be the case, you know, but then there are other forces at work, all right? So it could be that all of a sudden you'll get money coming out from nowhere, but then something else is happening. You're either really putting money in the system, then you'll have to keep track of it, okay? Or you're creating inflation by printing money. You know, then you can say, well, on a nominal rate, this won't work, you know, because this price here is not the same as this one because, you know, this money here is different money than that money there. Then it won't work. Now, because it inflated somewhere in this DT amount, right?
But that is the whole point of energy as a cash flow, right? You're constantly putting money in the system, but the energy stays conserved.
No. You're saying it quite wrong. The point is that you're not constantly putting energy in the system. The energy is the same. The surplus is the same. Okay? It's just that if you take the whole thing, what's happening, and you move it over a year later, the calculations will be the same. You don't all of a sudden get more income just because you're at a later time. All right? You understand?
Yeah, I understand that, but okay, just only the shift in time and not the whole time.
Yeah, you're thinking an evolution over time. That's okay. You know, energy can go up and down, but you can't take, you see, this is all DTs. There's a little shift in time here. Not, you know, huh? Okay? You can.
The energy is cash flow, so if you shifted a year, then you have a year of all that cash flowing in.
No, but time is going infinite, you know. Don't worry. What you can call this 2021, or you could use another calendar like some I don't know, Maya calendar. It don't matter what you call it. All right, huh? You know, that's what it's saying. All right. So you do this economics and you start this business, it doesn't really matter whether and if you have some profit motive or something, it doesn't really matter whether you do it today or tomorrow. The laws of economics will be the same, all right? Now you can say maybe that's not the case and this, well, that's not so interesting. What we do is we assume they are the same because that's why we call them laws of economics, and then we go and fit everything so that it works, all right? And that's the same with energy. So the old timers, they lost energy. I mean, they're doing all this work and then the work is gone and this plow is not moving with kinetic energy, so the energy is lost. And they thought that it would be lost, okay? So they said, well, it does depend on time because I took some time to plow this field and now all my energy is gone. And then it took them a while to figure out that it's not gone. That when you plow the field, that all these little atoms that make up the soil, they're all moving around like there's no tomorrow, right? And the total net effect of all this movement that has no net momentum, by the way, that is called heat, all right? And that was figured out much later. But here we don't have any heat yet, okay? We just have work and kinetic energy, all right? Huh? So here we have work, or this handling costs, right? And we have surplus or profit or whatever you want to call it, gains, huh? All right? So it's like a lot of these things, you know, like it's all really simple. You work your way through it, and then it takes a while for you to see that there's a really enormous amount of stuff going on here. It has to be understood, all right? And the analog with economics can only be understood if you understand it at this level. All right? So income is just expenditure. You know, your losses are going to be equal to expenses, you know? And your gains are going to be equal to your income. Right? So you can have I remember in the market, when I was on the market, you had these clever guys, and you know, you have these shares, you know, you can buy, securities you can buy, and there's always the question of what you want. You want capital gains or you want income, all right? So you want the price to rise or you want it to deliver a dividend, all right? So these dividends, they're like work, all right? So you get this is the different rate, the dividend rate, and this is the amount of the you know, the amount of the dividend, but the number of shares over which you're paying this dividend. All right, you can work this out. But you can say, well, I'm not gonna pay out a dividend. Well, then something that has to happen is the price has to go up. All right, okay, you have no choice. That's what happens. The price will rise. In fact, when a stock goes ex-dividend, the price drops exactly with the dividend amount. Boom. Huh? So it's just saying this. Now, the problem is that dividends are taxed at one rate. So in Holland, they will be taxed in box 1, you know, which is regular income. And capital gains are taxed at another rate. So in the Netherlands, we tax it in box 3, which will be over your entire assets, where they impute a sort of income, and it's kind of complicated. And in the US, they actually calculate the realized capital gains. Okay, so that is this. In Holland, it's really weird because they do it on unrealized, so they don't tax the surplus. It's something that's really not tenable because you can really only tax the surplus. So in any case, you will tax the capital gains, but in the United States, I think they are changing it now, but it used to be 15% rather than 50%. So what people wanted to do was they didn't want the dividend, they wanted the capital gain. So what they will do, they will set up a corporation, throw all the shares in this corporation, and they will get a special status for the corporation so it doesn't have to pay out the tax. You can get that. And then all the dividends would accumulate in the corporation, and they would sell the shares of the corporation to investors. That's called a SICAF, and they have them in Luxembourg. So it was a way of taking the dividend and turning them into capital gains so they can be taxed at a lower rate, okay? Right, so, but all you're doing is taking the tax out. The tax is just, you know, energy you're taking out, all right, of your returns. So this game was always played, you know, so you look at the total return. The total return is the income you make plus the capital gains that you make. And the one is your kinetic energy, and this, the other is just the work. And we'll see exponential energy. All right? And this is saying it's equal. This is, there are a couple of theorems in finance, is the capital structure irrelevance or something. You probably know about that, huh?
Yeah.
Modigliani-Miller theorem?
Yes.
Yeah. So if you're a corporation, you can finance yourself in two ways, either by issuing shares, all right? So you just sell yourself, right? Or by issuing bonds, you know, taking out a loan, and then you have to pay interest, all right? Now, this all will take us to the rotational analog, but the principles are going to be the same. One of them is work, and the other one is kinetic energy, is operational surplus, and this is a sort of potential surplus, all right? But the capital structure irrelevance theorem, or Modigliani-Miller, says it doesn't matter what you do, right? Huh? So there's tons of theorems in finance that come down to this business of conservation of energy. Now, also, you know, now these things are kind of independent of time. It doesn't matter, right? It's only when friction comes in that time becomes important, all right? And this is also one of the reasons power is not talked about as much in analytical mechanics, because they don't deal with friction, right? So for them, time is just sort of an arbitrary parameter that's indexing the path, and then they make time in such a way that the motion can be described in an easy way. You can define velocity and force as a simple time derivative. All right? Okay? So this is a picture, and I messed it up a little bit. Huh? So this is what I would call, again, this is what I would call the pricing power, some kind of power. Only because it's this thing that's changing. Huh? I don't really know whether they use pricing power that way, right? These things get bandied about in finance or in economics. I've never been able to find a good analog for power that kind of covers it. Now you can call it activity. We'll see that it also has to do with redistribution of income or surplus and dissipation of the surplus. So I tend to just use power, and then when I see, hey, the price is changing, there must be pricing power, whatever. But I confess that this is not very well thought out. Okay. Now we're going to do the next slide after the break. So I'm going to leave this slide here for you to look at. And then we can take a short break. All right? And then I'm gonna try to apply this stuff to actually get the kinetic energy, the co-energy, which Kunyan and others thought was the energy, and then summarize everything what we've done in these bond graphs. So that will give us something to do. All right? Okay. I'll see you.